Okay, so we're going to continue our look at precipitation reactions in this video, but here we're going to be focusing on the electrolytes in the reaction and how the way that we represent the principal characteristic of electrolytes, which is that they dissociate. Strong electrolytes dissociate completely, and weak electrolytes don't, is basically what's going on. So weak electrolytes, the extent of dissociation is very, very small. So the thing that's mostly present is the actual compound form of the electrolyte. The dissociated ions aren't really there. And so that's going to inform the way that we make our choices here. Okay, so we call the double displacement reaction and the overall reaction. It's just the terminology. Um, and so if we think about what happens is that both of the things on the left-hand side of the equation are always going to be strong electrolytes. So if we think about the strong electrolyte sodium chloride, we know that there's not really any sodium chloride present as a compound. Instead, what we have is dissociated sodium and chloride ions that are separated out in the solution. And the same thing is true of the silver nitrate. It's a strong electrolyte. And so both of those species are separated out in solution. So when we mix these two things together, we get one pot of solution with all four of these ions present. And so then we have the other two possible combinations that can form. And from a previous video, we saw that the sodium nitrate is still a strong electrolyte, okay, but the silver chloride isn't. And so we're going to write all strong electrolytes as fully dissociated the same way we did on the left-hand side. So the sodium nitrate is written as separated ions because it's a strong electrolyte. Silver chloride is a weak electrolyte, so we just write it as silver chloride. And this representation, where we write all strong electrolytes as dissociated, is called the complete ionic equation. So the next thing that we can consider is if you look, some of the ions are in exactly the same state on both sides of the equation. Here, the sodium is dissolved in solution. Here, the sodium is dissolved in solution. And the same is true of the nitrate, right? Nitrate is dissolved on both sides of the solution. I mean, since sodium and nitrate salts are always soluble, then sodium and nitrate are pretty much always spectator ions. Okay, so spectator ion is the special term we use for the ions that stay in solution throughout the reaction. The idea is that they're not really doing anything chemical in the reaction. They're just sitting there watching the other ions do things. Okay, so the same cannot be said of the silver and the chloride, right? The silver and the chloride start out when they're in two separate vials dissolved in solution. But when they get mixed together in the double displacement reaction and form the new silver chloride pair, that's a weak electrolyte and it comes out of solution as a precipitate. And so if we write what happens chemically and focus only on the chemical changes, we would write this form right here. So we've got a chloride ion combining with a silver ion to make silver chloride. That's called the net ionic equation. And as I just stated, you remove the spectator ions from the complete ionic equation, and this allows you to focus on the species involved in the chemical change. So the next example we're going to look at is the one from your discussion question, which was lead nitrate reacting with potassium iodide. So when this happens, you get a really nice looking yellow precipitate. Okay, and the overall balanced ionic equation is, balanced equation, the overall double displacement reaction is shown there. Okay, so what I want you to do is take a minute, pause the video, and write the complete ionic equation for this reaction. Focus on writing each side one at a time. So first write the left-hand side and make sure you've got everything included, and then write the right-hand side. Okay, that's a good way to break it up. Okay, so if we look at this, the complete ionic equation, the lead nitrate is going to come apart into a lead 2 plus ion and 2 nitrate ions, right? That's what this means. Essentially, you have 2 separate nitrate ions. You need 2 copies to balance the charge. So when they come out, they're going to go their separate ways, and we're going to count them as 2 separate nitrate ions. And the same thing happens with the potassium iodide. you've got 2 copies of it from the stoichiometry, so you're going to get 2 iodides and 2 potassiums when this comes apart. Okay? On the other side, the lead 2 iodide is going to stay together as a salt, so there's no change there. But this potassium nitrate is, again, a strong electrolyte, and so it's going to dissociate, and you're going to get 2 copies, one potassium counted twice and and a nitrate counted twice, right? So you get 2 copies of your potassium nitrate written as a dissociated strong electrolyte. Okay, so now identify the spectator ions. Take a second to do that. Well, it should be pretty quick, right? The sodium or the potassium and the nitrate are the spectator ions. You can see you've got your 2 nitrates here. You've got 2 nitrates over here. So you have the same number of nitrate ions in exactly the same situation. That's what we mean when we say a spectator ion. It's not doing anything chemical between the reactant and product sides. And the same is true for the potassium. Okay, so potassium and nitrate are a spectator ion. So now you should be able to figure out what you need to do to generate the net ionic equation. Take a second and do that. All right, so the spectator ions get removed from the complete ionic equation to generate the net ionic equation, just like in the last example. And so what we end up with is this case right here. So essentially we just have the lead 2 plus and the iodide that combine to form the lead 2 iodide solid precipitate, and that's our net ionic equation. Okay, so the one additional point to make is that occasionally you will have a case where there's no precipitate formed. Okay, and so in that case, there would be no net ionic reaction. Essentially, net ionic equation. You combine 2 strong electrolytes, and they stay strong electrolytes on the right-hand side of the equation because there's neither of the new combinations that you draw in the double displacement reactions is a weak electrolyte or is going to be an insoluble precipitate. If that happens, you just write no reaction. Here's a quick example. If you think about sodium nitrate and potassium chloride, okay, well, sodium nitrate is going to dissociate into sodium and nitrate ions. Potassium chloride is going to dissociate into potassium and chloride ions. But if we swap it, you're going to have sodium chloride, which is certainly a strong electrolyte because it contains sodium, and you're going to have potassium nitrate, which is certainly a strong electrolyte because it contains both potassium and nitrate. So your new combinations don't give you anything that can be a precipitate, so you're just going to have these 4 ions in solution on both sides of the chemical equation. And so all ions are spectator ions, and that's another way of saying that there's no precipitate formed, so there's not going to be a net ionic reaction, net ionic equation. We're just going to write no reaction. Okay, so now you can go on to the discussion question for this video, which is on net ionic equations.